All right, in section 2.2, we're going to really talk about more about the electrons and how the electrons are arranged. All right, Bohr was actually a student of Rutherford, and he didn't like the idea that Rutherford was saying that the electrons are just randomly all dispersed throughout the atom. He didn't like that. He kind of took what people have been talking about with light. Light, they came up with this concept of photons, which is kind of a bundle of energy, a packet of energy. Right? It's not really a particle. Lights really aren't particles, but they did call the particles photons, but they were more like wavelengths of energy. Einstein did a lot with this. Actually, he won his Nobel Prize for this type of concept. And I believe it was actually Einstein that coined the term photons. So this was kind of a start of a new branch of physics. All right, we have the classical model of physics. All right, classical or what's called Newtonian. All right, and then we have the newer model, which is called, and a second type, which is newer, probably about 120, 130 years ago, is called the quantum mechanics. That's an N, quantum. Okay, and this is kind of the difference, and it's a little weird. Imagine you are throwing a baseball. All right, here's you, and you have a friend that's over here that has his mitt. All right, and you're going to throw the baseball. All right, and you throw it with a certain amount of speed, and you can follow the path of the baseball all the way to your friend. All right, or your friend is able to follow that path. You can see at any moment in time where the baseball is because you can follow the path and the actual speed. All right, in quantum mechanics, that's not how things work. And this is kind of what all came out of this, is that the ball is either with this person or the ball is here. It's nowhere in the middle. You don't see it. You can't follow its path. It's either here or boom, it just appears over there. All right, and you have to have a certain amount of energy in order to do that. Like I have to put in a certain amount of energy in order to throw the ball. Now, let's just call it like E1. Okay, I need this amount of energy in order to get to my friend. If I put too little energy, then the ball just kind of falls down there. If I put too much energy, then the ball will go over his head and it goes over here. But I can follow its path and it will exist at these places. In the quantum world, if you don't put enough energy in, it doesn't go anywhere. It stays right there. Okay, you have to put in exactly E1 amount of energy. If you put in a little more energy, okay, if you put in like E2 worth of energy, that's fine, but it's not going to exist over here. It's still going to exist at your friend. All right, so if you throw a ball in the quantum world and you have this amount of energy all the way to E2, it's just going to appear with your friend. Now, if you have another friend out here, all right, and you put in this amount of energy, then the electron starts here and then it ends over here. It exists over here. It just appears. You can't see it travel there. All right, and these are what's called quantum numbers or quanta, where it's a certain amount of energy in order to get there, and that's kind of how light all behaves. And Bohr was really the first one who kind of took this information from the photon world or the light world and kind of established it. All right, just to kind of give you some ideas, light travels at 3.00 times 10 to the 8th meters per second. All right, now that's a big number. You might not realize it's a big number, but let me kind of give you a visual. In 1 second, all right, light can travel around our planet 7.5 times in 1 second. So if you if you turn on a flashlight and turn it off in 1 second, okay, all right, that light in that amount of second that you turn it on and off travel around the planet 7.5 times. Think about how fast that is. I mean, it like boggles the mind to even think that it exists. Okay, so as soon as you turn a flashlight on and you turn it off, that light hit you 7.5 times while traveling around the planet. Okay, light years. Everyone hears this term light years. A light year is if you're traveling at the speed of light, it will take you a year in order to get there. All right, our closest star to us, other than our star, is Proxima Centauri. All right, a lot of people think it's Alpha Centauri. Alpha Centauri, I think they thought was the closest star for a long time, but now because of more powerful telescopes and things like that, we've actually found another star. It's not as bright as Alpha and Beta Centauri. It's called Proxima Centauri, and that's 4.25 light years away. That's the closest star to us. All right, so if you're traveling at the speed of light, it would take you 4.25 years in order to get to that sun. All right, so just kind of give you an idea of how fast light is and how vast our space is. All right. So what Bohr did is he came up with these pathways. He kind of had like a circular model, which is not totally true. He had our nucleus here, and then he had these energy levels. He had an energy level here, an energy level here, and then a third one out here. He called this n equals 1. This is n equals 2, n equals 3. And he says the electron either exists here or it exists at the next higher energy level. It does not exist anywhere in the middle. Okay, he called these orbitals, these paths, and electrons want to be in the ground state. So if I have one electron, okay, it will exist in the lowest energy orbital that is possibly available to it. Okay, if this orbital is filled up with its maximum electrons, then the lowest energy for the next electron would be n equal to 2. But if I had an electron at n equal to 3, which is a higher energy orbital than it could exist in. It could exist in an n equal to 1. It's going to pop back down and release energy. All right, that's the radiation versus the absorption that we talked about. That's the radiating energy as soon as that electron pops down into the lower energy level. I think the next slide actually shows you this. Perfect. Okay, you see kind of your energy levels. Here's n equal to 1. All right, you can hold a max. Now, you can't hold unlimited electrons in n equal to 1. All right, you can only hold a maximum of 2 electrons, and this is what other scientists have found. 2 electrons max in there, 8 electrons in n equal to 2 max. Okay, 18 max, and 32 max in n equal to 5, 6, and 7. So 4 is 32, 6 is 32, 7 is 32, and so forth and so on. Oh, there we go. Okay, so let's just kind of take a periodic table, and this is kind of where things are going with it. I'll kind of show you where we're going with this. Okay, these are what's called electron configurations or orbital diagrams. Okay, you've got hydrogen right here, and you've got helium right here. And then the next level, you've got lithium right here and beryllium. And then you've got boron and carbon and nitrogen and oxygen. Okay, so hydrogen has 1 proton, has 1 electron. Okay, what's the lowest energy orbital that it could exist in? Okay, it can't exist in anything 2 or higher because I have this empty orbital. It wants to be in its ground state. That's what ground state implies, its lowest energy. So hydrogen is going to have its electron in this energy level, n equal to 1 energy level. Okay, helium has 2 electrons. So remember, I can do a 2 maximum. I'm not going to have 1 here and 1 in the 2 because that one can actually pop back down and be in a lower energy level. Okay, that's what they imply by the lower energy level or a non-excited state. Excited state would be if this electron popped up into here. Now, when we get to lithium, lithium has 3 electrons. So where are all those 3 electrons? Well, 2 of them are in the lowest energy level. I can't put any more in here, so I got to start filling the next energy level. So the third electron, so that third electron is in shell equal 2. These are called shell numbers as well as principal quantum numbers. I'm kind of giving you a heads up as to what we're about to see. Okay, and then the other 2 are in shell equal to 1. Okay, and this is kind of what he proposed, and it actually turned out to be pretty correct. A lot of other scientists saw this, but this circular path concept is not totally true, okay, which we will talk about in a second. All right, so basically if an electron, and kind of how you show electrons is by a half-headed arrow. So if the electron were to jump up to a higher energy level and exist in the higher energy level, it can actually pop back down and release that amount of energy. It would radiate whatever wavelength it was in order to excite it up there. And this is the example that I showed you. Either the ball exists here with me, or if I throw it or put enough energy in it, it exists with this, but it doesn't exist anywhere in the middle. Right? Or if I put in a lot of energy, it can exist here. If I put in tons of energy, then it can exist here, and then boom, it exists there. Okay, and then it can fall down various levels. It doesn't have to fall down each level. It can fall down. It can jump 1 and go to there, or jump 2. It just all depends on what the atom is and what the circumstances are. We'll talk more about this, but this is basically where we're going with this. It's what's called the electron configuration. It's kind of the zip codes to the electrons. Okay, so according to the Bohr model, when energy is added to a sample of hydrogen atom, so everything he did was with just the hydrogen. It worked perfectly with hydrogen. As soon as he did it to other atoms, it completely failed. None of the numbers worked. So this model is based off of just the hydrogen atom. This is what we talked about. It absorbs a certain amount of energy and then it gets promoted to a higher energy level. It's called an excited state, but it doesn't want to be an excited state. It wants to come back. It wants to come back down. So it comes back down. It relaxes and it turns that energy into an electromagnetic form of radiation, like light energy. And this is how fireworks work. All right. So imagine I have like sodium inside of a firecracker or firework. All right, sodium, it kind of has like a yellow color, a yellow/orange color. All right, well, it absorbs electrons once you heat it up. So the electron, it goes from one energy level to another one as soon as it hits the fire, and it's now in the higher energy level. Then it relaxes back down and goes back to this energy level, releasing the yellow color wavelength. Okay, so that's the excited versus the relaxed wavelength. And this is kind of how they kind of explained all this. It's like if I were to take a piece of metal, kind of another concept is, and I heated it and heated it and heated it, at a certain point, it can't absorb any more energy. It just can't absorb any more energy. Well, based on the classical model, it should be able to absorb an infinite amount of energy, but it doesn't. Why is that? Well, it's because the atoms in there only have a certain amount of energy levels. It can't absorb any more. So it's like our baseball model again. Once it absorbs a certain amount of energy, that's it. The electrons can't exist anywhere else. Okay? So this is kind of the limitations to Bohr's model. I'm not going to get way into the theory of Bohr, all of the things of the Bohr's model. If you take a higher chemistry class, you can talk about it. But one of the big things is that this perfectly worked for the emission spectrum of hydrogen. Okay, it's elegant. You see how they say that it elegantly describes the hydrogen, but it fails to explain everything else. Okay, so it turns out when there's more than one electron, the model is more complicated. And it's true, but you know what? This kind of gave a start to understanding electrons and how the electrons are all composed. Okay, so de Broglie was actually the one that postulated that if energy can behave like a stream of particles called photons, then under certain circumstances, electrons can also have these particle and wave-like properties. So Bohr basically said electrons aren't particles, they are just waves of energy. De Broglie said, well, you know, if you're going to say it's kind of like photons, well, it's going to have both. It has wave-like and particle-like properties, and because of this planetary model that Bohr kind of came out with, where you have a proton and then you have shell 1 and shell 2 and shell 3, is not totally true. You have these region of space called orbitals that the electrons exist in. They aren't particles that actually go around a nucleus. They're waves of energy that kind of are in a given area. Okay, so I believe this is kind of a model of that. So imagine you have a sparkler. Imagine an electron, okay? And an electron either exists here, or it exists here, or 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 here. All right. And again, it's not traveling through here. It just exists. It's there, and then boom, it appears there, and it appears there. Well, what they found is that it stays within a region. It doesn't just, like, I will not have one way out here and another one way out here and just random. It kind of exists in a specific region depending on the amount of energy. So 90% of the electrons are in a certain area. That's the region. That's what's called the orbital. Okay, and it's basically, it's kind of this area of energy. It's not really a particle. It's not this one electron. It's a wave of energy. It's an area of energy. So if you see the sparkles, you see, so here's an electron, here's an electron, here's an electron, here's an electron. You see how they're showing all these little things are electrons, but most of the electrons are within this region right here. So it's basically saying that the electron in this energy is actually mostly existed in this area. You see how they kind of show you. So that is the orbital. That's kind of what the electron looks like. It's this wavelength of energy. A perfect example that I like to give is, imagine you have a barbecue, okay? So you've got a barbecue, and you have it on. It's really hot. If you look at the top of the barbecue, so imagine that you are eye level of the barbecue. Let's kind of draw a barbecue here. All right, here's like the propane tank and all that stuff. Okay, all right, and if you look at the top of the barbecue, you kind of see this radiant energy that is coming off. Okay, it kind of wiggles, like if you look like past it, it kind of like the air is kind of like wiggling. Okay, I think you know what I'm talking about. Imagine an electron. Imagine I take a circle out of that, okay, and I bring it over here. So I have a circle of this wiggling energy, okay? That is what an electron is. That's the best way to describe this concept down here. You have this wiggling of energy, but now imagine I take a sphere of it and I move it around, okay? That's kind of like the best way to actually describe what an electron actually looks like in this map of electron probabilities, saying, you know, it's probable I'll find the electrons in this location. Okay, and these are called orbitals. Okay, yeah, okay. So again, shells, I've already talked about the principal energy shell. So kind of going back to the Bohr model, I've got the nucleus, I have shell 1 is the lowest energy, n equal to 1, and then shell 2, all right, and it goes all the way up to shell equal to 7, all right, the principal quantum number is what they call it. These energy levels, so within the principal quantum number, so within n, you've got these other levels, and for some reason they gave them letters. I don't know the history as to why. So for n equal to 1, you only have an s subshell. So here's your shell. This is your subshell. Okay. For n equal to 2, remember you can fit more electrons. They go in your s subshell first, then they go into a p subshell. For n equal to 3, you've got an s, a p, and a d. For n equal to 4, you got an s, a p, a d, and an f. Okay, so you can actually keep filling all these. Shell equal to 5, same thing, s, p, d, f. Okay, shell 6, you actually go back to an SPD. I'm not going to talk about it, but basically you now have a shell. Okay, so I have shells, all right, that are split even more. So I have shell 1, I only have an S. Shell 2 is split into 2 subshells, or 2 energy levels, S and a P. So shell equal to 3 is split into 3 different energy levels, and so forth and so on. Okay, and this, okay, yep, and this kind of shows that to you. So it's kind of a little bit more in detail. For shell equal to 1, these are your shells. It's only split into an S, which S has a spherical shape. Okay, P, all right, and a number of orbitals in that subshell. So we'll talk about orbitals in a second. Okay, then you have shell equal to 2, which you'd split into an S and a P. All right, S has 1 individual orbital, P has 3 individual orbitals. So I have a shell, a subshell, this is my subshell, and then this is my orbitals. Okay, shell equal to 3 is split into 3 different subshells, an S, a P, and a D, and these are the number of orbitals inside of them. I'll kind of show you. An S we kind of draw as a box. A P is 3 boxes. Each box can hold 2 electrons. So 2 electrons on here, 6 in here, so 2 here, 2 here, and 2 here. All right, in a D you can hold 10 total, so 2, 4, 6, 8, 10, because it's 5 different orbitals. And then in F, you've got 14. 1, 2, 3. So it should be 7. 1, 2, 3, 4, 5, 6, 7. 2 here, 2 here, 2, 2, 2, 2, 2, for a total of 14. Okay, and this is kind of showing you the F subshell, and it's split into 7 orbitals. Okay. So here are the shapes. I kind of showed that to you. So any electron in an S subshell kind of exists in a spherical pattern. Anything, and also as you go higher into your shell, so here's shell 2, this is shell 3, shell 4, it gets larger because you have more and more electrons in that area. P's have this figure 8 shape to it. Okay, you either have on the x-axis, you have on the y-axis, or you have on the z-axis. So that's why you have 3 different ones. You have one on the y-axis, one on the x, and one on the z, and it has like a figure 8 shape to it. All right, right now, if you're confused, don't worry. It will all come together. I promise you. I promise you. D has 5 different sublevels. These are the shape. Most of them have a clover. Sorry about this. This is my cat is getting a little too close to me. Sorry about that. Let me get him down. Okay, so you've got these clover leaf shapes, and then you have this weird one that's kind of like a p orbital that has like a donut in it, is kind of how they talk about it, and those are the F's. We are going to talk about the D's, okay? So let's kind of pause it there, and we'll come back with the next video.